Hello.
Hi.
Welcome.
Good stuff, Harris.
This is great.
We did something so awesome, we burned out a HDMI cable. Turns out that was the problem. So, sorry everyone, we're starting a little bit
Slightly late.
Good thing we left lots of times for questions, so we'll still have a little bit of time for questions at the end. Over to Paris.
Hi everyone, welcome to our Science Week session, which is Let's Train an AI. We're going to talk about and demonstrate how a real life AI works, real life, inside a computer. We're sorry for the slight delay. We broke an HDMI cable and then being computer experts, spent 20 minutes panicking. It was a really good, fun time for everybody involved.
Trying out the cable.
Speaking of the people involved, this is everybody involved. I am Paris, this is Mars, this is Tim, and behind the camera, away from the camera right now, but you'll see him in some activities later on, is Dr. John. Please
More cables than man.
More cable than man, Dr. John. Please feel free to tweet at any of us during the show, and we will probably ignore it because we're too busy panicking about the HDMI cable.
We'll reply later.
We'll reply later.
Snarkily.
And we might be able to answer some questions at the end, so feel free to. We're in Hobart. We're broadcasting to you from Hobart. Presumably most of you are also in Hobart. We hope you're in Hobart. It's a lovely city. It's beautiful. If you're not in Hobart, visit Hobart when you're allowed. Please note, this presentation has some content that resembles spiders. Some people
You didn't give the warning yet.
Well, it said spiders.
Some people are scared of spiders, so we're putting that up front. If you are alarmed by things that move in a spidery fashion, there will be some of that in this presentation.
They are not spiders, but they do skitter.
Yeah, they freaked us out a little bit,
So
we just put a warning
we'll
up.
give you a little warning before we do that, if we remember, but just FYI in advance.
Okay, so let's get cracking. We're a little bit behind. So this is policy, proximal policy optimization. This is the core of what we're going to be talking about. So I mean, this is actually, kind of bog standard stuff. Hopefully this is all really, really straightforward to you. I mean, this is the core equation for what we're doing here. I mean, the core things I really want to talk about today is the hyperparameter epsilon. You'll normally have that somewhere around 0.1 to 0.2. A hat t is the estimated advantage at time t. Is there any questions at this
Obviously,
point?
this is very simple. We'll get
Really
more
simple
advanced
stuff.
as we go.
No, we're just kidding there. What we're really going to be talking about is about this level of maths. We're thinking sort of stonks level is about as complex as we're going to get. If we do need to get a little bit more complex, that we'll try and point it out in advance. Hopefully this should be approachable for anyone. So what we're actually going to be expecting, we're going to be expecting some giant walking spidery robots. We're going to have some laser guns, because there's a lot of laser guns. We're going to have some explosions. We're going to have a few numbers, just a few. We're going to have a little bit of computer science. We're going to have some graphs, because you can't do computer science without graphs. We're going to have humanity being defeated by machines, because let's be honest, it's going to happen. And then we're going to have some more graphs, because at its core, AI is about graphs.
So let's get started for real. What do we think about when we think about AI? What comes to mind? Well, most people, when they think of AI, they think of this sort of stuff. Your robot characters from film and TV and games, whether they're good or bad, even though these usually have human-like levels of intelligence and autonomy, and usually the fact that they're a robot is more a plot point about them being evil arbitrarily or having special abilities. Or it's things like this, where somebody says, I made a neural net read / watch / whatever, and they brought out something that was slightly missing the point of the original content, or is a bit nonsense. But none of these are actually what we would call AI for the purposes of this talk. Obviously the movie examples are written by a person in a script, and those aren't real things that exist, but they're a little bit beyond our abilities right now. There would be thousands of systems to make something that complex, even if we could do that. And the menu and script examples were actually written by the author themselves. We find lots of these things where people say online, I made a neural net do X. Many of them are false.
Fakery.
They're generally quite funny, though.
What we're calling AI is generally a collection of algorithms that solve problems that are complex and that humans can solve, such as recognizing objects. So we can see here, this might be something that a self-driving car sees, where it needs to know that that's a person and not in the middle of a road that it's allowed to drive down. They're not always reliable, such as this example, where we have a picture of a cat that to a human looks like a cat, has been perturbed in ways that they've slightly tweaked every single pixel in a very specific way, and now the neural net that was trained to recognize what is a cat and what isn't a cat is absolutely certain that that is a bowl of guacamole.
My favorite thing about that is it turns out if you just rotate the cat picture just a little bit, it's a cat again. So it's so easy to trick these things. Just a little bit, suddenly cat.
Right, so we're going to talk a little bit about video games. AI in video games is generally just a list of rules that a human has written like a human, much like Dr. Tim or Mars or me, and they're told exactly what needs to be done. So most people's exposure to AI is actually in video games these days because they're playing against bots that are reacting to them, or they're playing against characters that are reacting to them. These are really just a list of rules. They're not really AI, so to speak. So that's how most AI in video games works. By contrast, what we're doing today involves artificial neural networks and reinforcement learning. This is what most production AI, so AI that exists in the real world, that is actually artificial intelligence by the technical definition of it is. It involves training a neural network, an artificial neural network, to do something. And that's what we'll be looking at today. Artificial neural networks are very fancy, complicated things that were invented in the 1950s by very clever boffins. Boffins are scientists. I'm told not to use that term by my editors sometimes. Artificial neural networks work similarly to our brains, where there's a giant web of interconnected neurons. It's kind of a vastly simplified system, but it's a good representation. Neurons have an input and an output. Some neurons connect up to things like eyes and sensors, or actuators like arms and legs. And stuff goes between these neurons, and then something happens at the end, like an arm moves, or a limb moves, or a joint moves.
It's worth pointing out the actual biological neurons are way more complex, and biologists and neurologists are probably freaking out going, what? They're way more complex. They are way more complex.
These idiots off the internet.
But it was still very impressive considering that
at
at the time their computers weren't powerful enough for them to actually run any
Any
good
of
one.
And it's a good conceptual
So they
model.
just went, wouldn't this be a good idea? I think.
Yeah. But it's a useful thinking model. It's similar to our brains, although our brains are way more complex.
So this is kind of how it works, sort of, but not really. It's a tricky bit to visualize. Observations happen, so like the world is perceived somehow. The thing that is perceiving the world can do something. It can affect the world somehow. It might be able to move its limbs slightly. It might be able to move towards something. A vast spectrum of possible actions something can do. And a reward happens. In our brain, rewards are the chemical signals that tell us what we're doing. In a simulated artificial neural network, the rewards might be a bigger number. So bigger is good. So these artificial neural networks, they can see or do things, and then they get rewarded for seeing and doing those things. And seeing might not necessarily be seeing. It might be monitoring a number and acting on that number. Everything boils down to numbers, usually. The computer then learns, based on what it's seeing and doing and how many rewards it's receiving, what it should do more of. Basically, like people.
That's where that big, long, complex number comes in. It learns using that big, long, complex formula.
Realistically, all we're talking about when we talk about AI today is a reward maximizer. AI, really, real, genuine computer AI, is basically getting a computer to solve some sort of repetitive task by rewarding it appropriately when it does the task using only minimal guidance. Make sense? Let's move on.
So to show you how a modern AI is trained, we're going to do that. We're going to train one here, on stage. We're going to train an AI who happens to be the Honourable Michael Ferguson, MP, Minister for State Growth, Minister for Science and Technology, Leader of the House, Minister for Infrastructure and Transport, and Minister for Finance. But here he's playing a robot, so we're going to call him the Ferginator.
We didn't ask permission to call him the Ferginator. Michael, we're very sorry. We love you.
And we're going to teach him that he should walk forward to reach a goal.
Let's cut to John out in the field.
Minty. Oh, good. Another minty. Fantastic. Yep. Hey, no. Seriously?
So we did this with rewards. We clearly encouraged some behaviour by giving him a treat and taking away a treat, and he quickly realised what it was we wanted him to do, even though we didn't tell him to.
So that was super simple and not even slightly degrading to a lovely professional, a politician like Michael, who was a very good sport. The Honourable Minister Ferguson, very lovely sport, very helpful. Not at all degrading though to act like a very simple robot artificial intelligence.
Not at all.
Not at all. But this was very simple. So now that we know the principles of how we make a thing move forward, in this case, let's see how we can make that work in the context of a video game or a piece of video game technology. So the way we train an AI using video game technologies, we use the same tools that people use to build video games, which are called game engines. In this case, we're using one called Unity. We create a virtual environment, we create a virtual robot, and then we tell the robot some facts about its environment and update the robot based on what it does. And we reward or punish the robot, much like John was rewarding or punishing Michael, based on what it's doing, and then hopefully, with many, many cycles of this process, the robot will eventually learn to do what we would like it to actually do.
We can hope.
We can hope. So we'll move over to our demo, and we'll switch a cable over here just to do that.
Okay.
Rip the dead cable.
We had 2 cables, but now we only have 1 cable.
Entire technology empire.
Crumbles by a single cable.
You tell me if you can see it.
Cables are very complicated. So now we have a single up, which is a mirrored desktop.
Yep.
An extended desktop, sorry, currently. And we're going to mirror our desktop, and you'll see our demo.
Cool. Okay. So, let's get cracking here. Let's see if I can make this a little bit bigger. There we go. All right, so this is our virtual environment. Like Paris said, this is a game tool called Unity. We're using this one because we tend to find it works very well for us, but you could do this in any virtual environment you wanted in. What we have here is we have our little robot friend here. That is our robot Michael Ferguson equivalent. And the reward is going to be the distance to the orange cube that we have there. So it can move forward and back, and we'll just see how it goes. We did a really, really super quick training where we trained it for literally less than a second, and we'll see how it goes by default. Let's have a look here.
Just going to fire that up.
See what happens. And, oh.
It's not very good at all.
Well, that's not very good. And that's because it hasn't learned, and that's okay. That's not its fault. So we're going to quickly toggle a few switches here, and we'll set it up ready to learn.
We really want this robot, our virtual Michael, if you will, to go towards the orange cube.
So we're just going to tell this to
Minister
start
Ferguson.
training.
The virtual Honourable Minister Ferguson, who is
Give that
an amazing sport. Big supporter of science.
Fire up tensor board as well, because we'll need that. So this is now going. This is ready to go. We now click play. And this will now look terrible because it's going to be running at about 1,000 times speed. But what we actually care about is this. Ooh, look,
We
charts.
promised there were lots of graphs and charts.
Oh, look. Let's make this one bigger. Cumulative reward is going up. Ooh, it's very interesting. The loss is going down, though, correctly. Let's check how many iterations it's done. It has done 5,800. So it's been doing this 5,800 times now. It's also worth pointing out, because we're monsters, every time the robot succeeds or fails, we kill it and start it again with its brain memory from before. So it's kind of like some sort of nightmare environment. Okay, that is now finished. Yep, there we go. I'm just going to grab the brain that it created here and drag it into Unity. I'm then just going to quickly...
This brain file is a representation of all the inputs and outputs that it received and what it feels like it learned from a particular training session.
Okay. And now, last thing I'm just going to do is quickly turn off training, because I've forgotten to do that before, and it looks very silly. And now, if we play it one more time, he should just zoot straight towards the end.
Basically a genius now.
Look at him go! Yay! He is an absolute genius. I love him. Good job, little robot. And that was trained in real time. You saw that happen in real time. That was, there was... real time, it took, maybe 2 minutes of real time, and we got to look at some very pretty charts here. Like, ooh, look at that.
It wasn't intelligence.
Look at that value loss. That's pretty good. Look, it's straight down. That's what you want. So we'll switch back to our slides now.
So that was our little demo there. We just trained an entire AI with an entire neural net of its own to solve a very simple problem, which was move towards the orange cube on a very simple plane. We could have saved ourselves a lot of time, however, by not using AI in this case, and written ourselves a very simple computer program that was basically hold down the key that makes the robot go forward. And we would have had to implement some code to make the robot go forward when you press a key, but the fact remains that we could have just told the robot to go forward, and that would have been a much more efficient version of solving exactly the same problem we just solved using artificial intelligence. However, computer science is very prone to implementing artificial intelligence into things where it's not needed. So we did it the hard way because we're computer scientists. We'll move on and explain how this makes sense. We're going to try something a little bit more challenging. So we're going to go back to Tim and his demo machine in a second and do a more challenging example of this, so we couldn't have just written a simple step-by-step program to do this.
So what we want to talk about now is drinking a glass of water. So when you think about it, what you've got to do when you're drinking a glass of water is there's actually a lot of sort of different steps involved. So if you want to grab a glass of water, you've actually got to, could we get the camera please? You've actually got to sort of, let's pretend our microphone, I'm not going to actually pick up the microphone because that would sound terrible. So you got to think, hang on, so this arm has to stretch forward until it's at the right position. then it has to close these fingers around it, and then it has to pull them back and then put it. It's actually a really complex thing. There's a lot of different sort of steps there. So that would be too many steps if you actually think about it for you to work out and write down a program to do it. And that's where an AI is going to come in. And we're going to see how hard that is. So we're going to make the Ferganator, or the Honourable Minister Michael Ferguson, Minister for State Growth, Minister for Science and Technology, Leader of the House, Minister for Infrastructure and Transport, and the Minister for Finance, drink a glass of water.
If
For
you're
that,
from
let's cut
outside
to John
Tasmania,
out in the
Tasmanian
field.
ministers have a lot of titles because they work much harder.
We'll cut to John out in the field.
Elbow inwards. Rotate wrist upwards. Rotate wrist upwards. Shoulder out. Shoulder forward. Elbow forward. Forearm up. Wrist right. Wrist left. Wrist left. Elbow inward. Wrist inward. Forearm inward. Okay. Elbow up. Wrist inward.
Okay, so if we look at sort of what was happening there, basically we had the Ferganator and, well, the combination of Ferganator and John see the glass and then have a series of steps that would tell them to rotate shoulder and elbow, and then basically check, are we closer to our mouth? That's basically the reward signal. How close are we to our mouth? Now, you don't really think about that when you're doing it as a human because we're very complex and we've got a lot of interesting things. But the process, you know, is a slightly fancier version of that, is how I would sort of think about it.
Just thinking about it, if you optimize for that, you just
You would actually, yeah, you wouldn't do it quite like that. So we were sort of observing the distance to the glass. So in this case, John was being the brain here. He was also, and then we had the Ferganator updating angles of joints based on what his brain, aka John, was telling him for doing, and then he was getting rewards by moving the glass closer and closer. So that's sort of how we would take this real-world environment and adapt it to something digital, pretty simply. Now that was way harder. As you could see, we may have spilled water on a minister, we may not, who knows. Let's take this idea a little bit further, and we're going to look at walking. We're going to do walking because it's actually slightly easier than grabbing things, and we don't have time for that.
So let's apply the same ideas to our little robot. We're going to teach it how to walk. So what's involved in walking? Well, we need to bend our hips and our knees and our ankles, and very specific angles to carry our weight. We might need to counterweight a bit. We've built a robot. Actually, John built a robot. We've given it some legs. It's a bit skittery. And we're going to teach it how to walk to a target object, the cube from before.
Spider warning.
Spider warning.
This is very much our content warning for spiders. If you do not like things that move like a spider, now would be the time to look away.
We're going to teach it to move like a spider. So how can we set it up so it learns to walk? Well, it's a matter of deciding what observations it can make of the world, what actions it's allowed to take, and then what it's rewarded and punished for. So the observations that we give it is what position all of the leg segments are so that it can move all of its joints at different angles, and how close it is to things near it by angle and distance. So it can see things, but it doesn't know what... Well, it can sense things, but it doesn't know what it's supposed to go towards. And then the thing it can change is the angle of each of its joints. So it doesn't know walk, it doesn't know step. It's a much lower level thing than that. But then it's rewarded for facing at the thing it's supposed to be going towards and also moving towards it. So that distance is decreasing. So training this with 8 legs took about 4 hours on John's laptop. And it's basically running at 100 times speed here.
That's why it looks a little blurry in that picture. It's literally running 100 times faster than normal.
I think this is a video. Anyway, it starts out moving completely randomly because there's no concept of walk, let alone walk towards something, but it eventually learns how to stand up because when it stops falling over, it's going to get some rewards for facing in the right directions by accident, and then it will learn to walk and then run and turn around. It will get so good. It's like an expert spider. And then we've seen it do some quite complex things, like it can do a somersault, and we've seen it fall over and it can learn to get back up again.
Seen it walk
things
over
that would be
obstacles.
way harder than teaching it just how to walk on a flat surface with no obstacles. So as the robot trains, back to our graphs from before, the amount of reward it receives increases, which means that by the metrics we've given it, it's doing better.
This is the stonks bit. Up is good.
So it gets points for facing towards the thing and for moving towards the thing. So if it got more points, that means that it probably got closer to the thing. or spent more time going towards it and then circled around it just to bugger with you. You never know. So we can see that at some point it stops getting considerably better, and that's where we can say that it's probably about as good as it's going to get. It's probably gotten perfect at the task we've given it to do.
So now we're going to cut to the laptop again. I'm going to hand the HDMI cable over to Tim.
See our little robot, terrifying robot spider son walk. I don't know why I've made him a he, but apparently I have. We've plugged that in.
So we'll just get the laptop back on the screen for you, and there you go.
Cool. All right.
We're ready to
So
go.
we're back here in Unity. Why do you keep going small, Unity? Never mind. We're back here in Unity. We've got a slightly different setup here. We've now got our kind of creepy-looking spider child here. There he is. Again, I don't know why he's a he. He's not. It's a robot. And I'm just going to click play, and we'll start watching it sort of running around. Wait a second. So here it goes. It's actually walking. It's walking towards the orange cube. Now, it's worth pointing, we actually make the orange cube move, because if we don't make it move, then it'll kind of just is a slightly more confusing version of the previous robot, where it was just driving forward all the time. Because if the cube didn't move, all it would learn is how to face towards the cube and then run in that direction. Now it had to learn how to turn. It's got these sort of two different numbers up top. These are the actual reward signals. So these are the Minty equivalents from before. In that the first one up the top there is facing, which is how many reward points it's getting for facing the cube. So if it's got the same facing, it gets more points, whereas if it's slightly off, it gets less. And if it's completely the wrong way, it's going to get negative points. And then approaching is how many reward points it's getting for getting close to the cube. So literally the closer it gets, the more points it gets. The further away, the more points it loses. And as you can see, it's actually really good at this. Now, it does do a few weird things. It's sort of a little bit jangly. It sort of jumps almost, but I mean, spiders kind of jump a little bit if you look at them. Part of this,
a really clumsy spider.
yeah, a clumsy spider. Part of this is because it sort of has, like, even humans, we got like these bone things, bones, I think we call them, but we've also got like sort of like flesh around our bones, which kind of acts as shock absorbers. This doesn't have these. Spiders are kind of fluidy as well, so they kind of have shock absorbers, which this doesn't. So it sort of hits the ground very hard and bounces a little bit, which is why it walks a little scary. But it's also like only 4 hours old, and I haven't seen many 4-hour-old kids walk well. So I think he's doing all right.
We just want to emphasize here, for those of you that might have a background in like computer animation or computer graphics, this has not been animated.
None whatsoever.
This is a spider-like object that is rigged to have joints in the appropriate places, which has then taught itself to walk based on the reward system we've given it in order to chase the cube, which is why it kind of moves slightly strangely compared to a real spider.
It's also worth pointing out the only thing it knows is where the cube is and the angle of its legs. That is literally it. It knows, oh, the cube's over there and my legs are like this. And then it's worked out how to walk, how to run, how to sort of jump and turn, all by doing this. So
We might switch back to the
might
slides
switch back
now.
to our slides now.
Just hand the cable, pass the cable back and forth.
Yeah, so I mean, that's our robot there.
Goodbye, Spidey.
Bye, Spidey.
We have our slides up. So, brilliant.
So the first thing you do after you build a robot is, of course, you give it a gun. The reason you give it a gun is because it's a robot.
This is
Inherently evil.
It is inherently evil. This is also a video game engine, and much of the video game world, like it or not, revolves around adding weapons to things. So we figured, in the interest of demoing this to people who might be familiar with video games, using the technology that we've used to build it, we'll add a gun. It turns out that teaching a thing on a computer game type system to kill isn't that hard. The gun will actually have...
Read into that what you want.
Yeah, the robot overlords are going to come for us eventually, but they're not quite here yet. Teaching a thing isn't hard. Well, actually, what we've done here is we've given the gun a separate brain. So in this context, we have the walking thing, which has its own brain, which knows how to walk, or has learnt to walk and track the cube. We also have a gun, which has its own brain. It has the observations of angle to target, so it kind of knows the angle towards the cube. That's it. The gun has one action, fire, or no, fire. And
We
the
don't have
gun,
sound.
there's no sound. The gun gets a reward for hitting the target, again, which is the cube, and a punishment for not hitting the target.
Now, this wasn't the only way you could do it. There are some advantages and some disadvantages doing it this way. The reason we did it this way is because it's by far the simplest to train, because we could train the walker how to walk by itself, then train the gun how to shoot, and then we can just mash them together, and they don't actually have to be together intelligent, they're just accidentally together intelligent, if that sort of makes sense. It's just much quicker to train them this way, which is why we did it.
So we're going to switch back to the demo now. So just forgive us while we pass the cable forward.
If it works. And we're back,
Our
hopefully.
laptop is now connected.
There we go. So we're back in our old friend Unity. So this is the exact same scene we had before. The only difference is I have turned on a gun on the robot. Otherwise, it's exactly the same. And like I said, the gun's got its own little brain. And I'm just going to click play here. And we can watch as it's going around. It's running and it's shooting. So one interesting thing is the brain isn't particularly smart on the gun, so it just tries to shoot through obstacles. So it is wasting a little bit of its time there, but that's okay because it is so fast at shooting that it doesn't matter. It just got bashed by the cube. It's so fast at shooting that it doesn't matter if it occasionally hits obstacles because it'll quickly track. And you can see it's destroying them almost quicker than we can actually see it. So I'm just going to minimize that there. I'm just going to sort of zoom in here on the different view.
So every time it successfully hits the cube, a new one appears in a different spot. That's totally random.
And we're just sort of zooming out so we can watch here. It's just absolutely annihilating these cubes as we go. The only thing it's doing that's a little weird is it doesn't understand that occasionally there's obstacles. And that's only because it's only a few hours old. Like, we didn't spend forever teaching this thing how to be a truly brutal killing machine. It's just sort of incidentally brutal killing machine.
I can't see obstacles.
Can't see obstacles. It's also worth just pointing out really briefly here, in this scene, we've actually got 9 of these. The reason we're doing 9 of them is because it's just faster to train them when there's lots of them. So we're training multiple of them at once, it's just quicker.
Lots of computer science problems become much easier to tackle if you do a lot of it in parallel. And basically what we're doing here is we have 9 scenes, all feeding the observations and actions and rewards into one learned brain.
Meta brain.
Which means we can train it a lot faster.
It's like a time tunnel.
Oh, yeah.
Same brain.
Yeah, same brain, yeah, I like that description. It's time tunnel. So we'll jump back to our slides
Different
now.
action paths.
Just jump back to our slides while we hand the cable back and forth. Please forgive us again. I'm going to play those slides now. Excellent. So, what we've just learned is that robots are fantastic at murdering small cubes, and they will be the death of us all. No. We're going to have a bold attempt to fight back at the robots now, just to show you how we've connected all this together in a game engine, and that you could go and do this too. We'll put a link on the YouTube video later, which will live in perpetuity, where there's some resources where you can learn how to do some of this stuff yourself. So we would typically do this in a live audience and bring an audience member up right now, but because we're all stuck inside at the moment, we're going to use Mars.
Oh no.
Who's going to fight the robot for us. And what we're going to do to fight the robot is we're going to hook this controller to the video game.
It hooks up. Connected. And we're going to plug in our cable
So we'll just
again.
switch the cable again while Mars familiarises herself with the controller.
I've been told
Tim?
I can move and A is shoot.
You can also aim the gun.
Yes.
It's your
I
standard
can move
sort of...
and I can aim the gun and I can shoot.
Alright, so this is sort of practice mode for Mars. Can you just sort of... Ooh, can you just try going around? Yep, okay, cool.
We'll switch to the computer,
give a quick
and
shoot.
then this. Oh,
Yep.
God.
So this is
Inverted
the bottom
controls.
screen is Mars'
Try
thing.
now. Is that correct?
Yes.
Yep, there you go.
Okay.
See, we're playing for that.
So is that? Am I facing backwards? Gun? Go.
That's
go.
forward.
Okay.
Yep, see, you're facing that way.
Okay. I need
So
to
we'll
face
give
the
Mars
gun
a practice
perfectly
shot.
forward.
Mars is our best hope for humanity, so we should probably let her have a little bit of practice. Okay, so I think Mars has got this ready. I think let's actually, we're sort of going to go for it. So now we're going to add the robot in.
Come back here.
And
Cube.
we will see what happens. They're going to have 90 seconds. We'll see who gets the most. Our terrifying spider bot son will be at the top of the screen, and Mars will be at the bottom.
I'm
So
ready to fight for humanity.
you can do this, Mars.
All
Okay.
right.
There we go. He's in. Oh, so he's currently at 3 points to 0 for Mars. 5,
Where's it
6,
going?
7, 8,
No.
9. I'm just going to stop calling these out because I think it's going to win. Come on. You got to get one of them.
Yeah.
Go. Yes! Okay, that's 1 point
Every
for
time
Mars.
we've done this, the human has not done a very good job.
I think
Go
I've got
back
the
here.
best at 8 from memory.
Yeah, 8 is about the max I've ever seen happen. It's,
Oh, you missed.
I'm shooting at you.
You're actually shooting backwards, I think.
No, I'm not.
Did you? Oh, no, okay.
she's got 5 now.
Oh, she's got 5. Oh, she might beat my record.
She's scoring. She's scoring.
Oh, 5, 6. Oh, hang on. Oh, no. Oh, 7. Oh, no, she might beat my record. That's terrible. It's actually good, I guess, because... Oh, 9. Nice. New record. Can you beat it? 40
Give it up, I'm
seconds.
moving the gun.
40
It's too
seconds, Mars.
confusing.
It's only 28.
Ah.
Okay, it's now 30. 31. Okay, all right. You can still claw this back.
Nope, I've just gone the wrong way. Come back.
If you look, the robot isn't even moving that much anymore.
I know, I
It's
should
just
just see which
so
way
good.
he's shooting, and that will tell me what it is. Come back! By the time I see it, he's already got it.
19 seconds left, Mars. You can do this. You've only got to get 32 more kills.
I'm just gonna shoot randomly. Go! Come back!
The idea here is to show you just how fast this robot is.
10! Double digits!
Doing what it's been trained
And
to
remember,
do.
this was trained in less than a day. It was trained
Come
in a
back
few
here.
hours on a normal laptop, not any sort of like supercomputer or anything fancy. Oh. Okay, so with a final score of 53 to 11.
That's actually pretty good. That's
actually, I
high
think, the best we've ever seen. Actually, if we just cut back to the scene here for a second, you notice the robot is still just annihilating the cubes. That's because it doesn't actually know that the game has ended. We never taught it about game being over. The robot is
somebody else is playing.
It's just so hardcore that it's just annihilating
What do you
anyway.
do? You kill cubes.
Yeah, it just kills cubes. It does not care about anything else. Doesn't care there's another player. We actually had to disable the physics system a little bit because we noticed in some early testing the robot was walking up over the top of you as the player, and it was just way too creepy. So we had to turn that off. Also, I suppose ramming the robot would probably be a good strategy if you could do that.
Very much so.
We don't want to give the humans an unfair advantage. The
It doesn't
robot's
give a
already got
single
a huge
bother
advantage.
that you exist.
Does not even know you
Walk
exist.
on your head.
So we're just going to switch the cable back now.
Do some wrapping up. Being very carefully not to drop the cable so I don't have to duck off the camera to
If
pick
If we
it
kill
up.
another
Silly.
one, you're going to have to demonstrate the spider's
Okay,
movements yourself.
So our
Making
presenter
spider noises.
slides are back up.
Okay.
So I did my best to defeat our robot overlords, but I still failed
We didn't
by
actually
a
even-
large margin.
We didn't even
So,
write an all hail our victorious human overlord slide
We
because
didn't have to.
we knew it wasn't going to win.
Because once you train an AI to do a specific thing, it can usually get near perfect. So it could far exceed the human performance at a very specific task, but it will never learn to do something else. So thank you, everyone.
If anyone has any questions, please feel free to message us through. I have one question from
Oh, yes.
Paul in Hobart.
Paul? Hi,
Would
Paul.
like to know how long it takes to train something that's actually really complicated and why it takes time to train. So it's like 4 hours seems like a long time to Paul, and he would like to know why.
So that's a very, that's a really
I
complex
was going to say
question.
animations are among the most complex things that you can train a single neural net to do, because like even thinking about our 8 legs, if each one has 2 joints, and then it just has so many different reward signals. The network that has to control that is huge because the amount of observations it has deems the size of the input layer on the neural network. So you can imagine
About
that's huge.
5,000 neurons total, I think, from memory.
Yeah, so these kinds of animation spatial problems are usually far, far more complex neural networks than you would say, like image recognition, which are the other things that we think of as really hard.
I mean,
Plus there's image size.
So there's this new fancy thing called GPT-3, I think is the current number. It came after 2 and 1.
Yes.
And it took, like, weeks to train using, I don't remember the number, but gazillions of CPUs and GPUs, like literally millions of dollars, probably billions of dollars worth of hardware, trained by giant tech companies who have billions of dollars to throw at this stuff. And that took literal weeks to do.
One of
and
the
that's
interesting
after
things.
designing it.
One of the interesting things that somebody's just asked me about is why they've obviously done some research themselves. Why GPUs are used to train artificial intelligence. So, for those of you that don't exist within the computing world, a GPU is a graphics processing device. You know, if you have a video card in your computer to play video games, that is a GPU.
Yeah.
They are used to accelerate the 3D graphics on computers and things that have 3D graphics and that thing. But it turns out the kind of calculations you're doing to do 3D graphics and display really fancy high-end modern video games on your Xboxes and your PlayStations and your computers and your Nintendos are exactly the same kinds of calculations in terms of a math sense that are needed to create a neural net.
Specifically, they're all matrix operations, if you know what that is. If you don't know what that is, don't worry. I guess
Big
technically they're
numbers.
tensor operations, but that's just a fancy matrix. Don't
I was
at
going to
me,
say you
maths
could
people.
use video game analogies, which is the reason why we have a GPU and a CPU and a computer nowadays is that they used to be you had processing units, and then we realized very quickly that you couldn't get any more performance out of something that was a generalist. So we started to min-max processing units. We made a bunch of different ones that were better at specific jobs. So then we had them allocate different things. So generally we have the CPU, which is something that does generally everything, and sometimes they have specialized cores within it. Whereas nowadays we're getting like GPUs and TPUs and different processing units that are good at different things. And GPUs, the calculations that they use for video is just lots and lots of floating
Floating point operation.
Floating point operations, so decimal numbers, lots and lots of complex decimal number transformations, which is exactly the kind of stuff you need to do to compute a neural network. So it's the fact that a GPU is at its core just a really good floating point operator processing unit, and the fact that we use it for video is just incidental. So now the fact that we use it for machine learning is just incidental.
Incidental, yeah. There are dedicated, what are they called, tensor processing units, I think, yeah, which are dedicated hardware just for the purposes of machine learning, and they're awful graphics cards.
For some of the younger kids watching, or the older gamers watching, if you need to make an excuse to buy a really powerful computer with a good graphics card and you just want to play games, you could always say you want it from artificial intelligence because they're the same. So I think we have some questions
That's what I told my husband.
Exactly. I'm the husband. So I think we have some questions from the audience, which John is going to speak to you about from a disembodied voice that you will not be seeing.
Because he's in the field, remember?
Yes.
Hi, it's me. I'm from the disembodied void, and also I'm going to turn my levels down a bit.
Mr. Ferguson there with you?
So Ken J. Price asks, if you let the spider learn to walk a few different times, does it always acquire the same gait, or are there different styles that emerge?
Well, generally the initial state that a neural net starts from is completely random, which means that the point where you get a decision, division of paths can vary quite a lot. So the bigger the neural net, the more that variance can equate to, but it wouldn't necessarily be such a high level difference that you would see a completely different gait. It would just be that in each micro instance, every tiny decision on a single joint might perform completely different.
Yeah,
it doesn't mean that would end up looking like a very different spider.
Yeah, it does depend on the problem, I think. In the case of walking, you're kind of going to get the same thing every time. You're going to get the same thing, I think, every single time when it's a walking thing, or something that looks kind of similar. In this case, our spider had no concept of energy. So, like, me moving my arms and legs uses energy, and I need to eat to get more energy. Our spider doesn't have that concept, so it's actually a little bit more like jump happy than a real spider is.
We find that if you train something that has a humanoid form, bipedal, that it walks by flinging its arms forward because that adds momentum forward, which makes it move faster and have to worry about balance less. And the reason why we don't do that is it exerts a bunch of wasted energy.
Well,
but it
professional runners, for their brief moments, you'll actually, because they're sprinting, they'll actually be doing that.
But also, for the spider, we have like the uncanny valley effect, where we notice more minute differences in things that are humanoid than necessarily a spider, but then also a spider, we kind of know what a spider looks like, so we also recognize less minute differences in its gait than we would something that moved completely differently to anything that we would know of. So it might be that each spider we looked at is moving quite differently, but we all look at it and go, ooh,
it's a spider. Yeah. Humans aren't good at telling these sort of things apart. Which is
I'm not sure if John has another question from the audience, but I have one question that somebody's asked me.
Mm-hmm.
They've asked, what are the actions that the spider bot can perform?
Specifically, it can basically like pretend my arm's its legs. Hang on, let's use this arm.
This is for each arm.
For each arm, it knows it can move like this joint and this joint. Basically, it can sort of like move its elbow and its knee. Is the
so
word,
from I guess the spoke, it can move the whole leg up and it can compress the joint in the middle.
Yeah. And that's all. No, that's the only actions it can take, and the only information it knows is the current like angle of each leg, I guess, is the right way of looking at it, and its direction to the cube, let's say the microphone's the cube, and the distance to the cube. That's all it knows, and that's all it can move. So
because it did have, I don't know if we pointed out, that the spider does have a head that faces a specific way, and it can't move its head, so it does have the idea of a facing.
If you don't give it that sort of rule, so I believe in one of the early ones we trained, it didn't have a concept of forward, it was just distance. And that meant it tended to sort of like prance around like that instead of turning. And even though it actually worked fine, it just looks weird and looks terrifying, more terrifying than it already does. So it's much nicer to sort of just add a little bit of like, I guess I was going to say human motion, but spider motion into it to sort of encourage it something a little bit more natural feeling. But yeah, you don't need to give it that. It was just something we did. So it knows its angles and how to turn them. Those are the only actions it can do.
I have one more question, which is probably our last question because of the time, from Amanda in Launceston, who has DM'd me on Twitter. She says, am I right in assuming that the actions that the spider is taking are random and then it eventually becomes less random as the rewards happen?
Yes.
That's exactly what's happening. So the spider is taking completely random actions on all its possible action spaces, which are its leg movements, getting rewarded or punished accordingly, depending on whether it's achieving its goal, and then iterating repeatedly until it slowly converges on the optimal solution to the goal, which is getting towards the thing.
This
by,
is why the first thing that we saw that was just you could move forward and back towards a cube, it was kind of jittering on the spot. Because much like the first Ferganator example, until it had moved forward and backward enough times to recognise the pattern in the rewards they were getting, then it was just still experimenting to figure out.
We actually had to do 2 takes of the Ferganator's first one, because in the first one he just went, oh, I should just move forward then because I want more minties. So it turns out humans are really quickly at learning, unsurprisingly. So we had to be like, can you just be a little bit stupider? That would be great if you could just dumb it down a little bit, because he's just too smart and he figured it out straight away. But it is the same thing. We didn't tell the robot what to do. We just told it, these are your minties, have at 'em. And it went, oh, okay, I should do more of this to get more minties.
It's also that a human has some innate knowledge that like, oh, candy is good, candy is a reward. Without that knowledge, it doesn't know if the reward that it got for going forward could be exceeded by the reward for going backwards or elsewhere. It would get an arbitrary number. It would go, could I get more?
Yeah.
No. All right, let's do that then.
Yeah.
So that's pretty much everything we've got for you. Feel free to tweet at us at any time, including after this. Slides, please, John. Feel free to tweet us at any time after this. If you have any questions, we'll answer this at any point.
And we just wanted to say a special thanks to our helper, the Minister.
It was an amazing sport, despite that clip. So if you have any questions, feel free to tweet at us. Use the hashtag ScienceWeek so we can find them. We have some other content about this we'll tweet out later with that hashtag, so you can learn a bit more yourself, and we'll attach it to the YouTube video, and it will be available at the link you're watching it on in perpetuity, so you can go and watch it again. I really hope you enjoyed it. Thanks for coming.